In this video, we're going to demonstrate how sequential logic circuits can be used to construct a finite state machine. In previous videos, we discussed how combinational logic circuits allow us to make decisions. Using various gates, we can put a circuit that implements a specific truth table. Storage elements, on the other hand, can store individual bits of data, and combinations of these bits can represent individual states. So, putting together these two types of logical circuits can be used to organize a device which cycles through a series of states. Each state can be uniquely represented by a unique combination of bits in the storage elements. Combinational logic circuits can make decisions to what should be the next state. In addition to this, external inputs and external outputs can help us to control another device. Sequential logic circuits are building blocks of finite state machines, because when we cycle through states in a device, basically we're transitioning from one state to another state, and the combination of all states would basically organize this device as a functioning finite state machine. The finite state machines are widely used, and every computer and every digital device essentially is an implementation of a state machine. In our next series of exercises, we're going to build a finite state machine that controls, using its outputs, a set of traffic lights. So the states can be viewed basically as snapshots of some system with unique characteristics. Finite state machines is defined based on 5 unique components or elements. We have some number of states, we have some inputs, and we have some external outputs that we can generate from the state machine. And we also need to be able to gather and know all possible transitions that should be allowed between different states. Specification of all of this determines the external output value. In addition to this, we can say that we need to realize what events trigger our state transitions. So each transition describes what it takes to get from one state to another, with all preconditions and postconditions of that state. State diagrams are very popular in different areas of engineering and software. So here's a quick demonstration of a phone call state diagrams. It indicates that we have an initial state where everything is turned on, and then possibly for us this would be a handset taken off the hook. Then we have the dial tone. From the dial tone we normally transition to dialing, then connecting, then ringing, then talking. So these are all sorts of state transitions and states put inside individual bubble. Altogether, this is an example of a state diagram with events that trigger state transitions and with specific transitions that explain how we transition from one state to another. So here's another example of a diagram of finite state machine. This finite state machine has 3 recognizable states labeled X, Y, and Z, and apparently signals that it receives in each state, which could be 0 and 1, transition it from one state to another state. For example, in state X, when we receive a 0, we transition the state machine to state Y, and 1 transitions us to the state Z. So all of these transitions are described and indicated by what kind of signal triggers state transition. This transition right here indicates that a 0 transitions Y into the same state. So it's like self transition right here to the same state. In addition to just labeling our states X, Y, and Z, we also assign each state some unique outputs. This is in our own discretion what kind of outputs we would like to be able to provide out of these states, and apparently these specific bit patterns of outputs can be useful in some sort of hardware. State transitions are triggered by a clock signal. So there's normally a clock circuit, which is a mechanism that triggers these type of shape of signal, and the periods here are typically referred to as a clock cycle. So the state transition normally happens when the clock signal rises from 0 to 1. And then it lasts some period of time, and then it drops down, and then it waits for predictable interval of time, and then again it makes its transition from 0 to 1, triggering a transition to another state. So these periods are called clock cycles or clock intervals. And in digital circuits, the transition from one state to another state occurs at the start of each clock cycle, like I indicated. At these positions, normally we have a transition to a different state. So it's pretty simple that the clock cycle just generates signals 1 and 0. 1 triggers transition, and 0 allows to update internal state or internal information inside this device, and also provide us required interval of time before the next state transition takes place. In this video, we're going to create a state machine which implements animated danger traffic sign, which will have 5 traffic lights, and in one state, let's label it state 1, basically all of the lights are turned off. Say in state 2, unique identifier of state 2, one of the lights will be lit. In state 3, then we can light up more lights, and in state 4, potentially we can lit all 5 of these lights. And then if these identifiers are unique states, obviously the clock signal will transition us from one state subsequently to another state, and eventually it's going to cycle back to its initial state. We can also recognize another state which we could label a 0 state, in which basically all of the lights are turned off and the entire device is turned off. So this is like an off state. So obviously if the switch is turned off, then we could transition from any of these states to an off state at any given moment of time. So this is roughly the idea about the state organization, state transitions, how many states we need to create this animation, and the outputs of these states will allow animation of these lights. So this is an actual state diagram for the traffic danger sign. Okay, so basically the idea is that we would like to enable these lights to flash, and so here are the 4 states we need if we're using binary system for our identifiers and state transitions. Then all of the states have unique identifiers 0, 0, 0, 1, 1 0 and 1 1. So obviously we can see how these transitions, primarily signal 1 of the clock cycle, transitions subsequently from 0 0 to 0 1, and then to the next, to the next, and to the next. And here we show which lights are turned on in each state. So basically we light up these lights based on external output out of these states. It's just a description of the animation process based on transition from one state to another. And this diagram here describes how we could organize our device based on some combinational logic, just a very basic block diagram right here. So this is where we can make instant decisions, and this combinational logic will implement a certain truth table which will allow us to control these lights numbered 1, 2, 3, 4, and 5. There is a switch which can turn the device entirely off, and part of the truth table output will be cycled into the storage elements, which will be able to accept new values from the combinational logic circuit and be able to transition to a new state based on the clock signal. Once we make a transition, new state will be supplied back to the combinational logic circuit, which will generate new outputs, provide new set of lights for our animation process, and as well back circuit the new state, generate new state over here, and supply it back to the storage elements which represent the current state. The clock will cycle again, the new values will be accepted by storage elements, and then when the clock goes back down to 0, the new state will become available to the combinational logic circuit. And so this way essentially we implement a cycling through these states using these elements. So our external inputs are basically just one, for the sake of demonstration, is just a switch, turn on and off. External outputs control the lights. Internal outputs generate new states as we cycle through current states. And this block right here indicates our storage. As you recall, in the finite state machine, we need only 2 bits to identify our unique states. So we cycle from 0 to 1 to 1 0 and 1 1, and here these 2 elements will be storing these values, starting with 0, then going to 0 1, 1 0, and 1 1, and then back to 0 0. The next portion of this diagram demonstrates a possible implementation of programmable logic array with the decoder, which will be taking inputs from the switch, which can be simply 0 or 1, and the 2 of the elements. So these two elements are supplying their inputs. So this programmable logic array will be decoding these signals, generating unique value in one of these wires, and then basically we make appropriate connections, and we say that then we can control the lights by outputs 5, 3, 4, and 1, 2, and also we can generate a new state over here and cycle them back to our storage elements over here, and they will be remembered at each clock cycle as the new state that the device will go on. Now, the actual implementation of the 2 of these elements is visible right here, and this is our storage element, which is based on the circuit commonly known as flip-flop.